We will start section 6.4 by showing you how to solve a differential equations by using separation of variables. Here we have dy dx equals x, y quantity squared. We got both x and y in the equation, so we're going to need to separate them and put the y with the dy and the x with the dx. So we'll start by rewriting, making it dy dx equals x squared y squared. And then we'll separate and make it dy over y squared equals x squared dx. Now we'll integrate both sides. This becomes the integral of y to the negative 2 dy. Over here we still have integral of x squared dx. Antiderivative will be negative y to the negative 1 equals 1/3 x cubed plus c. Our initial condition, x is 1 when y is 1, so we'll get negative 1 equals 1/3 plus c when we plug in 1 for each x and y. C then ends up equaling negative 4/3. So my equation then will be negative y to the negative 1. We're going back to the equation that we got when we first solved it with the plus c in it, and we're going to replace c with negative 4/3. So it equals 1/3 x cubed minus 4/3. This is negative 1 over y equals, and I'm going to put the common denominator, put it together as x cubed minus 4 all over 3, so that now I can take the reciprocal of both sides and get negative y equal 3 over x cubed minus 4, which means y finally will equal negative 3 over x cubed minus 4. In our second example, we're going to rewrite dy dx as e to the x over e to the y, which will allow me now to separate the variables. I couldn't do it the way it was originally written, but we know that e to the x over e to the y is e to the x minus y, so we just kind of went backwards there. And now we'll have e to the y dy equals e to the x dx. If we integrate both sides, it will simply be e to the y equals e to the x plus c, our initial condition when x is 0, y is 2, so it becomes e squared equals e to the 0 plus c, which is e squared equals 1 plus c, which means c equals e squared minus 1. So we rewrite our equation. We'll go back to when we first solved the equation right here and rewrite it as now e to the y equals e to the x plus c, which is now we found to be e squared minus 1. All we have to do now is solve for y, which y is in the exponent. We'll use logarithms and get y equals the natural log, or log base e of e to the x plus e squared minus 1. Hopefully you all remember the direct proportion language you learned in Algebra 2. Here we see the rate of change of the population is proportional to the population. The larger the population, the larger the change is going to be. And so to write that in the language that we learned in Algebra 2 and Pre-Calc, we would say that dp dt which is the rate of change of the population, change in population with respect to time, is directly proportional to the population that's there right now, and so that would be time equals Kp. The rate of change of bacteria is proportional to the amount present, and that could be, again, that could be the rate, if bacteria, the number of bacteria is B, dB dt would equal Kb. The rate of change of the amount of money in account is proportional to the amount of money. So the rate of change of the amount of money, A, with respect to time, is directly proportional to that amount of money, A. And the rate of change of a quantity is proportional to the quantity. So that's the same in all of these. So all of these are the same type. They are called the law of exponential change. The law of exponential growth and decay is also, can be called, if it's, decaying. You also have already studied this in, like I said, Algebra 2 and Pre-Calc, but now we're going to provide calculus to see how it was all developed and how that all comes about. So here we go. Find the population equation, P of t, if the rate of change of the population is proportional to the population. So again, dP dt equals Kp. So let's take a look what would happen if we do what we just learned with separation of variables. dP over P would equal K dt. And if we integrate both sides, that will be the ln of the absolute value of P equals Kt plus C. The absolute value of P can just be written as P because P is a population, and that population has to be greater than 0. It's a positive number, so I can just write the ln of P equals Kt plus C without the absolute value. And when we do this, we always have to have some type of justification of getting rid of the absolute value sign, so make sure you make note of that. Now we want to solve for P. So what would P equal? Well, P is going to equal, this is log base E, so P is going to equal E to the Kt plus C. And from there, we can say that P is going to equal E to the Kt times E to the C, because with the same base, you'd be adding the exponents. So those are equal. We're kind of going backwards. We know that if t is equal to 0, then the population will be whatever the initial population is. And we could write that as P sub 0. But we also know that in this equation, if t is equal to 0, we know that P is equal to E to the 0 times E to the C. And since E to 0 is 1, P will equal E to the C. Well, again, that's P sub 0 because that's the initial population when t is 0. So the initial population is E to the C. So that means my equation is simply going to be the initial population taking the place of E to the C times E to the Kt. Now that should look familiar to you. You should remember something very similar to that you learned in Algebra 2 and Pre-Calc, and that would be A equals PE to the RT, the PERT formula. You can see that is where it comes from now. In general, the law of exponential change will be dy dt equals ky, which means that the rate of change of some quantity y is directly proportional to the amount of y that's present at that time. So again, we solve this using separation of variables. We'll have dy over y equals k times dt. And just like the last one, we'll integrate both sides, and we'll end up with the ln of the absolute value of y equals kt plus c. And once again, we know that y is greater than 0, so we can just say the ln of y equals kt plus c. And then this will be y equals e to the kt plus c. And that means that y will equal e to the kt times e to the c. We know that when t equals 0, that we will have the initial amount of y, and we call that y sub 0. We don't know what it is, but we just call it y sub 0. Sorry about that, can't write it very well, but anyway, we have now y equals e to the 0 times e to the c, and that would be y sub 0. And so that means e to the 0 is 1, so y sub 0 equals e to the c. In other words, my initial amount is e to the c, and so I rewrite the equation as y equals y sub 0 e to the kt, and that is how we basically can do it generically for any in the law of exponential change, what that equation is. In this problem, we're going to take what we just learned and use it in Newton's law of cooling. Newton figured out that the rate at which an object's temperature is going to change is proportional to the difference between its temperature and the temperature of its surrounding or surrounding medium. In other words, if you take something very hot and stick it in the freezer, it's going to cool off faster than if you stuck it outside where it was 75 degrees. So it's going to, the object's temperature is going to be a factor, and also its surroundings. So what we're going to do is let T equal the temperature of the object. That could be something hot you took out of the oven, hot coffee, it could be a pie, whatever. And we're going to let T sub S equal the temperature of the surroundings. The rate at which its temperature is changing is dt, capital T, dt, d capital T, dt, and that's proportional to the difference between the temperature of the object, T, and its surroundings, T sub S. So once again, we'll do separation of variables, dt over T minus T sub S will equal k dt. And just like all the other ones before, we're going to integrate both sides. This becomes the ln of T minus T sub S equals kt plus c. We know that T minus Ts is greater than 0 because if it's going to be cooling, the temperature has to be, of the object has to be greater than its surroundings, otherwise it would be heating up. So we know that's positive, so we have now the ln of T minus T sub S equals kt plus c. And if we solve that, we know that T minus T sub S is going to equal e to the kt plus c. And we will rewrite that now as T minus T sub S equals e to the kt times e to the c. We know initially when t equals 0, then capital T will equal the initial temperature at the beginning. So I'm going to put 0 in for little t and T sub 0 in for capital T, so T sub 0 minus T sub S would equal basically e to the 0 times e to the c, which means T sub 0 minus T sub S equals e to the c. And if I rewrite my equation, t minus this one right here, I'm going to rewrite as t minus t sub s equals e to the c is t sub 0 minus t sub s times e to the kt, and that is Newton's law of cooling. We're going to use Newton's law of cooling to solve this problem. We're given that a temperature probe or a thermometer is removed from a cup of coffee. It's then placed in some water that's 4.5 degrees Celsius. So our surrounding medium, or the temperature of the surrounding medium, is 4.5 degrees Celsius. 5 seconds later, after it's placed in that cup, we read the temperature on the thermometer to be 49 degrees Celsius. We wait another 5 seconds and read it, and it's 30 degrees Celsius. So it's cooling pretty fast. So we're going to use Newton's law of cooling to find the temperature at the time that the probe was removed from the coffee. In other words, right when you first plugged it into the water. What was the temperature right before you plugged it into the water? In other words, its initial temperature is what we're going to be looking for. So we put into Newton's law of cooling what we know. We know T minus the surrounding temperature of 4.5 is equal to the original temperature, which we are looking for, minus 4.5 times E to the KT. And now we're going to take the information they gave us and plug it in. When T is equal to 5, we would have the temperature of the thermometer is 49, so we put 49 in for T, minus 4.5 equals T sub 0 minus 4.5, and that was after 5 seconds, so we put 5 in for T, and we get E to the 5K. 5 seconds later, in other words, 10 seconds after we put it in the cup, the temperature is down to 30 degrees of the object, which is the thermometer, and that will equal T sub 0 minus 4.5, and that will be E to the 10K. So I'm going to take these two equations, the 49 minus 4.5 is, we're going to need to subtract that, so that's going to give us a value of 44.5, and that'll equal the T sub 0 minus 4.5 E to the 5K, and then 30 minus 4.5 is 25.5, which will equal T sub 0 minus 4.5, and that will be E to the 10K. So now I'm going to take those two equations, I'm going to take and divide the left sides, and I'm going to put the second equation on top so that E to the 10K will be on top. When I subtract it, it'll be positive. So I'm going to put 25.5 divided by 44.5 should equal the right side's divided. 25.5 divided by 44.5, since these are equal to each other, the right side, this, with the E to the 10K, should equal all of this, divided by all of this E to the 5K. So we're going to make this equal to T sub 0 minus 4.5 E to the 10K divided by T sub 0 minus 4.5 E to the 5K. And now we know these will cancel out. And we're left with the 25.5 over 44.5 equals E to the 5K. Solving that, 5K is going to equal the natural log of 25.5 over 44.5. And K then will be 1/5 the ln of 25.5 over 44.5. And we're going to take that value and store it in our calculator. And that way we won't be rounding. Do not round in the middle of these problems. The value you store in your calculator will be approximately a negative 0.11136. Okay, but we are not ever going to type that in. We're going to store that in for K in our calculator. You can use any letter you want, but I'm going to store it in for K. Now I'm going to take and write my equation with the K value in it. So it'll be T minus 4.5 equals T sub 0 minus 4.5 e to the negative 0.11136t. So we know that when the time is 10 seconds, t equals 10, we can plug 10 in for this t here, and we're going to plug 30 in for capital T, the temperature of the object after 10 seconds. So we plug those two values in, and the only value then we won't have is this T sub 0, which is what we're looking for. So 30 minus 4.5 is 25.5. And this will be T sub 0 minus 4.5 E. And when you plug a 10 in there, that's going to move it one place on the decimal, and it'll be negative 1.1136. Now we have to solve for T sub 0. We'll take the 25.5, we'll divide it by e to the negative 1.1136. Now once again, I will not be typing that in my calculator. I will have stored that longer value in for K, and I'll just type in e to the negative K, or whatever letter you want to use. And that'll equal T sub 0 minus 4.5. And so basically you take your calculator and do that division, add 4.5 to your answer, and you'll find your initial temperature is 82.157 degrees Celsius. Part B wants me to find how long it now is going to take the thermometer or the probe to reach 8 degrees Celsius. So we again just use Newton's law of cooling, T minus 4.5, the surrounding temperature, still the same, equals, now we know the initial temperature is 82.157 degrees, minus 4.5 times e to the negative 0.11136t. And we want to find out how long that time is going to take. So we're going to be finding T in this case, and the temperature is going to end up at 8. So that's what we plug in for T. We plug in the 8 because that's the ending temperature. We plug that in for T, and you end up with, when you subtract these, you get 77.657 e to the negative 0.11136t. Again, I'm going to use my stored value, and so this becomes 3.5 on the left side. We divide that by 77.657 equals e to the negative 0.11136t. So basically, the exponent, negative 0.11136t, will equal log base e, or the natural log, of whatever 3.5 divided by 77.657 is. So you punch that in your calculator, and you'll take the natural log, you'll divide by the stored value of k, negative 0.1136, whatever that stored value was, and you will end up with 27.832 seconds.